Yeah, there we go.
Thank you.
Thanks, Karen. So, hello everyone. So this is our tutorial session on the fourth lecture of the TYC Materials Modelling course. So this is your opportunity to ask questions about what I presented this week. So Zoom does have this chat box on the side, but it seems a bit tricky for me to see it when I'm screen sharing. So it's probably going to be easier if people are happy to just ask their questions over the mic, if they have any questions they want to ask. So I've got a copy of the slides, the lecture notes open at the moment, so I can run through the material again, but I guess it would be most productive if people have questions they wanted to ask. So I'll give you a chance at the start now. If anyone has any questions on the material that was presented, now's the chance to ask away.
Hi Tom, I have a question.
Sure.
I'm just wondering, so for the equation for the Bloch's theorem, you said that the exponential function of that's a function of k and r. You said it's not periodic, but it's periodic. Could you explain that? I wasn't really sure what you meant.
Yeah, that's probably a poor choice of words on my part. I should have been clearer about that. So some of these functions are periodic with the lattice vectors of the unit cell, which is what I meant when I said it wasn't periodic. It's not periodic with the lattice cells, the unit cell that describes the physical cell, but it is a periodic function in the mathematical sense of it repeats after a certain amount of whatever input argument it has. So I should be more clear about the distinction between something that has crystallographic periodicity, which this exponential doesn't, and things that are periodic functions in the mathematical sense, which this exponent is. Is that clearer, Daria?
Yeah, it is. Thank you.
Because when we say periodic in the sense of crystals, what we normally mean is that the crystal structure itself is periodic. Were there any other questions anyone wanted to ask?
Hi.
Hello, Victor.
Okay, I just want to ask a question on the slide 29, the equation 32. I'm not sure how to get the equation 32 from equation 31. Can you explain a bit on that?
Yeah, sure. So, oops, 1 second. Is it this bit in the notes, Victor? Is this the equation you're referring to?
Yeah, yes.
So, sorry, which step?
From 31, how did it become equation 32? Because I think there's a conjugate wave function, but I'm not sure how it disappears and becomes 32.
So let me refresh my memory. So this is the example where we have the kinetic energy dominated situation. So just put the potential to 0. So we've got a Hamiltonian, and we've got this substitution here. So the del squared of psi of r is equal to minus k plus g squared vk of r. Okay. What does that mean by VK? Oh yeah, sorry. I think it's come back to me. It's a normalized function. I think that's the relationship that's being used here. I can double check the maths properly and get back to you, Victor, if you want more detail about it. But I think that the important point here is that these real space parts are normalized. So if you integrate over the function in the complex conjugate by the normalization condition, you should just get 1. So I think that's what's happening here.
Okay.
Because the function's normalized to have 1 electron in it. If you take an integral over the whole function, then it should just return 1.
Okay, thank you.
I think this psi k star here is a mistake, I think.
Oh, yeah, that's why I wondered why there's a conjugate star.
Yeah, sorry, my apologies. I'll take that out. That shouldn't be there. Yeah, if you do the sum correctly, then the real space parts, as I say, if you integrate over the whole function, the both the function and its complex conjugate, by the normalization condition, it should just become 1, and that kind of falls out of the argument.
Okay, thank you.
So yeah, my apologies for the typo there. And did David cover this in his lectures as well? You probably did. Because this kinetic energy dominated limit is the same as the homogeneous electron gas, essentially. That's what produces these parabolas in terms of the free electron gas. Does anyone else have any questions?
Hi, Tom. Yes, I was just wondering, in equation 10, you expressed the R as like a multiple, and I was wondering, why can you do that?
Yeah, so this is oops. I need to get more monitors, really. Where was that? Here, this multiplication here in equation 10.
Yeah.
Well, yeah. So I think the thing here is that because these are exponential functions, if you let me say, easier just to look at the written down notes I have. We've got that this alpha function. Oops, is it alpha in the online copy? No, I used a different notation on the online one. Okay, but this function here is related to the fact that this function is just when you it's basically related to doing this definition twice here. So we have the idea that what's written in equation 7 here is the case that every time that we could the solution of this equation has to be the original equation multiplied by something. I forget what this letter is called. I shouldn't have used it. It was the letter in the derivation that in the written down version of this derivation I used. I changed it when I went through the notes by hand. But what all we're saying is we're just applying this identity in equation 7 twice. So if I was to apply just one shift big plus r, it would multiply this function by this function that depends only on big R. I'm just saying that if we do this procedure twice, then we should be the same as if we've just added the big vector R that's made up of the two components. So R and R prime. So the relationship has to hold whether you just add that vector in one go or whether you add it into two parts. Is that any clearer? I can also write out some stuff if that would be helpful.
Yeah, if you could write out some stuff, that would be good, because
Yeah.
I can't visualize it, I don't think.
That's not paint. So I'm not as high tech as David. He's got some sort of tablet on the go. But oops. Oh. So we've got this expression here to start off with, that psi r equals whatever this letter is, r psi. And the idea is this equation, I'm just going to change this to alpha, which is what I have in the notes. When I went through the derivation on pen and paper. But this has to work whether if we have this R vector is made up of two parts. Oops. Then yeah, it's a bit annoying actually. Maybe I should have denoted it like that. This definition we've got should work regardless of whether we apply these two vectors one after the other or whether we just apply them in one go. So if I was to take this expression and I was to add this R double prime to it, oops, it would look, I'd get a result that looks like this. Oops. So we'd introduce one of these multiples, but then if I add the second one, it would produce, you would just repeat the procedure. So you would end up with psi r equals alpha ri alpha r double prime. Oops. Psi r plus r prime plus r double prime. So what we've just, all I've done is I've just applied the same equation twice. The point is that this expression here should still be the same as if I just added this singular r. So you've got this relationship then that alpha r prime alpha r double prime is should be the same as alpha r. That's where the multiplication comes from. So whether we add this additional combination of lattice vectors, if we just add it in one go, or if we break it up into two separate components and apply them separately, mathematically that's the same thing. So it has to produce the same answer. So it produces this condition here on the way this alpha function is behaving, because it's a multiplicative factor as it is. It means that, yeah, you get this condition on the values of R, big R. So if I was to break up any particular combination of lattice vectors I add into two different combinations of lattice vectors, it should produce the same result as if I just added both those vectors at the same time. So we go back to the slides, is what produces this condition here. Which is quite quite a big constraint on what this function alpha can actually be. And that's what then produces the idea that it has to be an exponent function.
Thank you. Thank you. Yeah, that's clear now. Thank you.
Because whatever function we have in here, it has to respect, as I say, the property that, yeah. Well, yeah, okay. Hopefully that's a bit clearer. I could have neatened the notation off a bit on that. Anybody else got any questions? Well, I'll take that as we don't, so I guess we can just talk through some of these results, and if anyone has any questions as we go along, then please do shout them out. Oh, I should check the talk as well, shouldn't I? Okay, that seems to be right. I mean, really, everything that we're saying later on about Bloch's theorem and the solid state band structure kind of comes out of the different ways we can describe these sort of crystal structures. Because if we have a degree of choice about what this unit cell we define as, if any sort of like regular unit could be repeated to make a crystal structure, but then it's going to affect. So this isn't a unique choice what this cell is, but it affects how big the real space part of the system we simulate is. And that is directly related to when we start talking about K-space and band structure. It's inversely related to that. So the bigger a chunk of material that we choose to pick as our unit cell, the smaller the reciprocal space will be, and the less band structure will be present in K-space. But generally speaking, from a computational point of view, we want to use the smallest unit we can because it's more computationally efficient to simulate a small unit cell and then do some K-point sampling than it is to do the alternative. This idea of Bravis's lattices is a bit hard to imagine. I always found, but this is just saying that if you are making repeating patterns of dots in this, like the black dots we have here, there's actually not that many ways you can arrange these black dots such that you get a structure they're actually allowed by the 3D perfect periodicity. In fact, people have gone through this a lot, and they've worked out that there's only actually 14 different structures that you can make out of just black dots. But there's a lot more crystal structures than this that a crystal could have, because each of these black dots will be our motif of atoms. There will be there could be more than one atom placed on each of these black dots, so it leads to much more available crystal structures than just these fundamental Bravis lattices. But regardless of what you put in your unit cell, it's possible from symmetry grounds to already narrow down the relationship of the unit cell into these 14 types. Sometimes that's quite useful. But these are the three simplest ones, that the structures that come up a lot of the time, where you either have something like a sort of simple cubic arrangement, something like a body-centered cubic system where there's an extra atom in the middle of the cube, or something like a face-centered structure where there's atoms on each of the surfaces. So it's quite normal to use these three simple crystal structures, because these Bravis lattices become crystal structures if you just say each of these lattice points I just add one atom and use them as simple examples of the different possibilities. As I say, the way crystal structure works is you're always going to attach a motif of some type of arrangement of atoms to each of these black lattice points and then generate a crystal structure, which is the mathematical way of describing basically any of these crystal structures. So for these examples, the size of the unit cell is related. It's going to be one of these, essentially going to be one of these 14 Ravis lattices, but you're going to have some combination of atoms placed in it, which is what motivates us to look at the problem mathematically and try and understand what we could say about the wave function of system just based on the idea that the way the system is a crystal, is a periodic arrangement of atoms. And this is always related to this idea that if we add lattice constants, we're in the same place in the crystal. So if we jump back to kind of an example structure like this, the lattice vectors are kind of these sides of the square. And if we move any combination of these sides of the square, we should find ourselves in the same place. And from a physical point of view, these points are should be indistinguishable experimentally. It shouldn't be the case that some parts of the identical crystal are somehow different to other parts of the identical crystal. So we should have the crystal structure perfectly repeating in terms of these lattice vectors big R. And we should expect the operators on the quantum mechanical observables of this system to also display that same symmetry. So what you would expect, or at least what I would expect, is that the wave function would have the same symmetry as the system and the physical observables. This is where Bloch's theorem comes in, because actually it's a little bit more complicated than that. And this complexity comes out of the fact that the wave function's complex number, and the crystal symmetry which it's describing is all just describable in terms of real space without any complex part. So any imaginary component. So the wave function is a bit underspecified for this sort of crystal structure. What that means is if you were to just simulate this crystal in terms of just a real space block without using this idea of k-space sampling, you'd find that you get a better and better description of the crystal as you make this box bigger and bigger. So it's more able to reproduce the actual wave function of the crystal, because the wave function of the crystal itself is not it needs a larger object to describe it than just the crystal symmetry of the atoms. But if we run through the Bloch's theorem, this exponential part is still very tightly constrained in what it can be. So we end up with this exponent, which describes what's normally called the k-space of the material. But as Dario asked at the start, what I need to be clear about is that this exponent doesn't have the periodicity of the crystal lattice when you run through the maths, but it ends up being related to the reciprocal of the lattice instead. So in terms of actually being able to fully describe the crystal wave function, we need to fully describe its value at every point in the real space cell, but also at every point in the reciprocal lattice, the first Brillouin zone. And as we make our representation of the crystal larger and larger, this reciprocal representation gets smaller and smaller. So if you imagine that you're actually simulating just all of the atoms in the crystal directly, you wouldn't need to worry about k-space. It's only necessary because we used symmetry to reduce the representation of the system down. And there's these equations define exactly how you go from a real space cell to the reciprocal space cell that matches it. And they're a bit hard to visualize, but we normally just run through the first three simple examples. Like the simple cubic is kind of the special case where the reciprocal lattice looks the same as the real lattice. But there is one kind of distinction in that it's conventional to start thinking of the unit cell as the coordinates being defined at the bottom corner. But people always conventionally define the reciprocal space cell with the coordinate system in the middle. So this is actually a distinction that could be a bit confusing. But that's part of the reason that these reciprocal lattices often don't look exactly the same as the real space lattices, just because the coordinate system is shifted a bit. So that's how you get to situations like this, where you have a more complicated structure like an FCC lattice. Its inverse is a BCC lattice, So the reciprocal space looks like this. Again, maybe this doesn't look perhaps exactly like what we'd expect for a BCC lattice, but partly that's because the coordinates have been shifted so that it's defined around 0. And we often don't see the BCC lattice defined in terms of its actual minimal representation. So this shape in here is the smallest possible unit cell that can describe this BCC lattice. So it's got a bit of an odd shape. And we see a similar thing for the BCC structure, but it's the other way around. But yeah, I always found the most helpful way to think about the differences in terms of what this case-based sampling represents is to look at the two extreme examples that we can access mathematically, which in this case is where either potential energy dominates or where kinetic energy dominates. And we've always got to bear in mind that real systems are always going to be in the middle of these two extreme limits. So you can see that if you run through a derivation where you just assume that there's no kinetic energy, but everything's described in terms of this potential energy, you can see that you don't get case-based sampling in that case. So this is one kind of extreme limit, and it means that if you have something like you're using a periodic system to represent something like an isolated atom, as long as these isolated atoms are far enough apart from each other that they don't interact with each other, they'll be exactly the same as we'd expect from just isolated calculations. We'll just end up with hydrogen atoms with discrete energy levels. And these energy levels are localized to one hydrogen atom, and they don't have this kind of band-like dispersion. But yeah, thanks for the correction here. When we run through this argument in terms of something that's dominated by kinetic energy, then you get the parabolas of the free electron gas, where we find this case-based parameter is important. And this is kind of a bit related to the idea that electrons are sharing the same space. So there's a lot of them in the same space, but in terms of the Fermi exclusion principle, they can't occupy exactly the same states. So this case-based parameter kind of opens up an extra parameter to vary how these electrons fill the space. But as related to Darius' question, these case-based dependencies are periodic with respect to the reciprocal lattice vector. So the maths if we just go with the maths directly, there's a lot of redundant information that's included because you get one of these parabolas on every single reciprocal lattice point, and you just can keep on going infinitely. Same as the original crystal structure, it's an infinite symmetrical relationship. You would just keep on going. But in order to actually look at something that's easy to understand and contains all the important information, then it's conventional. Then just as it's exactly equivalent to when we have a unit cell, how you can think of the system just in terms of this unit cell of atoms and just mentally forget about all the rest of the atoms, even though they're still there. They don't add anything to the description. It's the same with the way these k-space is filled up by electrons. So you can just focus on this reciprocal unit cell essentially, just the section that's repeated over and over, and just look at that whenever you're thinking about how the electronic structure works. But then some of these parabolas we see in this reduced space are actually kind of the ones that are sensed on other lattice points, and that's how you end up with just more than just a single parabola in this kind of slice of the system. So just like the unit cell in real space contains all the unique information about where the atoms are, this particular slice of the bryons, the first bryon zone, contains all the information about how the k-space can be filled. And when we look at something more realistic, we kind of end up somewhere intermediate to these two situations, where you don't get perfect parabolas and you don't get perfectly straight energy levels, using MgO as an example. But the idea of K-space is actually quite useful, even though it starts off as a kind of mathematical element of in the equations. Actually, when you sit down and try and understand how solid materials work, and actually it's easiest to understand a lot of solid state physics in terms of this K-space parameter. Particularly, you get the idea of bands where there's particular energies where no electrons are allowed to be, because there's no available energy level at any value of this K-space parameter. Yeah, the interest in just looking at the band structure and looking at the band gap in these types of systems tells you what sort of material you have in terms of the way it interacts with electricity. And there is some approximation you can make in terms of how these bands are shaped, which is related to how well charge can conduct through these conduction bands and valence bands. Particularly, this is one of the really important results of solid state physics, in that it's actually easier than electrons to move through good conductors or good or through semiconductor materials than it would be if there was just empty space there. So you have a lower effective mass for these electrons. But when we're actually doing calculations in terms of running a DFT calculation, then we can't it's not normally done just to describe this K-space as a function. We need to evaluate it at some particular points, and that's the thing that people do. So there's kind of, when you do DFT calculations, there's normally two different sorts of calculations people do. Sometimes the K-space is sampled along a path, which is what you do to produce something like this diagram. And each of these points along here could be a different part of the DFT calculation, which is how you would calculate a band structure. And that normally requires quite a lot of calculations to generate some nice flicking band structure like this. But when people are doing day-to-day calculations and they're not primarily interested in what the band structure looks like, then they'll just use a grid of points to sample this K-space parameter. The most common thing to do is this Monkhorst pack sampling, where you just place a uniform grid of points in the reciprocal space. This is a simpler example in some ways, because I've just used it. This is a simple cubic Brion-Zane for the reciprocal space, but really these points should be sampled out of whatever really complicated shape you have like this for your Brion-Zane. But a computer is normally happy to work that out for you. This is an important convergence parameter for practical DFT calculations. So you need to use enough of these K points that it well samples this Brion-Zane, and you get a good description of the properties that you're interested in. It's just an example of total energy in diamond, where you can see that as you include more K points, you see it converges to a constant value, which we take as being the converged energy of the system. But K point sampling is annoying to do, because it sometimes gets better and it sometimes gets worse. It doesn't uniformly get better with the number of K points. This is quite related to the symmetry these K points have. They're not all going to be equivalent in terms of their symmetry. You often get an odd even effect depending on whether you sampled the middle point or not. And how many of these K points you need to actually reproduce the system you're interested in is going to depend on the physical description of the system. So if you've got something like an atom or a molecule, you don't need any K points. The other extreme limit is where you have a metal. Where metals, you require lots and lots of K points to describe the metal as well. You know, semiconductors and insulators are in the middle. Are there any more general questions in terms of what I've just talked through? Like, it's fun to ask more general questions about DFT. Yeah.
How do you actually sample different K points, physically change or to change your K value in your the simulations you're running? I don't know. It doesn't seem to have that intuitive a physical relation. Like, I'm not explaining myself very well, but say if you had something that's in between a molecule and a pure lattice, what would you change? What's your input parameters to tell you tell the simulation where this K point is?
So I guess, are you asking about this slide here, really? What I'm just saying here? How
Well, yeah, you have a rough guideline for how many K points, but how do you actually choose those K points as such?
Well, I guess there's two questions there which I'll answer. Tell me if it helps. Like,
yeah,
in terms
I don't know enough to ask the question properly, I guess.
I mean, like, the first thing is kind of that just because there's this mathematical freedom to have a strong dependence on K point on this K parameter doesn't mean that the physical system will actually use it. So that's what I was kind of demonstrating with the hydrogen atom.
Yeah.
Like, there's several systems that you can describe without these K points. It tends to be things like isolated molecules or things like that. In which case we don't need to worry about sampling these K points, because even though the mathematical freedom is there for the wave function to have this dependence on K, it doesn't actually use it very much. And I guess in the extreme opposite example is metals, where the band structure and K point dependence of metals is very complicated. It tends to be quite difficult to explain it correctly. You need to use lots of K points. And this is related exactly to this idea that the electrons in metals spread out over a much larger area. So if you have electrons like in a molecule or atom that are really well localized and they're not delocalized at all, then they don't tend to use this K-space parameter very much. If we have something like a metal where loads of electrons are spread out over the volume of the whole crystal, then it actually becomes really important to sample this K-space parameter. In terms of how you actually pick these points, a lot of the time it just comes down to this idea that if we have enough K points and we don't choose particularly biased K points, then it should describe what would happen if we just sampled infinite K points, which is what the mathematics would kind of demand. And if we add enough points in, then we should find for different materials that we get to the point where it stops affecting the results. And that's what the convergence test is. You check how many K points you can add until it just stops mattering. This choice of Moncourse pack sampling is kind of used most of the time because it's not biased about what points you pick.
Pick arbitrarily in space in a uniform. Yeah.
Well, it's not particularly biased anyway. It's not completely unbiased, but it's not particularly prejudiced. But and this goes back to these kind of more complicated band structures like this, in the sense that these what are called high symmetry points, which are what people have sat down and tabulated, are always going to be band maxima and minima. If you think about just adding more and more points into sample this volume, it gets more and more likely that you have points near all of the extreme maxima and minima, which are obviously important to have in order to describe your system. But in terms of just using a uniform grid, that is slightly just because it's the simplest thing to do. You can definitely argue that there's more intelligent choices of K-point sampling that you could make. You could try and very intentionally choose points that were important to the band structure you're interested in. But then that becomes a massive amount of work in itself, so people don't very often do it.
What I was really trying to ask was how you actually, not how you choose the points or why you do it, but more how you can do it, how you can make this reciprocal space vector an input parameter. For example, you have that plot with the hydrogen, with the K along the bottom for hydrogen atoms. And how did you change the K value for each of those simulations? Did you just plot a horizontal line in Python?
Yeah, so well, we can define a block wave like state. So this is perhaps a bit more what I discuss next week. But when you run a DFT but it's a good question to ask. When you run a DFT calculation, then you kind of have to make some choice of how you're going to describe the wave function. And when you're constructing your trial wave function, you can basically have a version of the wave function at every k point that you sample. And then it comes out of the calculation variationally how those different k points interact with each other, how it affects the result that you get. But there's no problem in terms of this mathematical expression defining a value of your wave function at every k point. That's how a code will do it.
Okay, I think that makes sense. So you just, it's an input parameter into your basis set almost.
Yeah, you can kind of think of it that way. It's
if you have plane waves, you choose the k values with those.
Kind of, yeah.
Choose, and then you optimize for the parameters.
Yeah, you can think of it that way. Yeah.
Okay.
But,
I should just watch six lectures, I guess.
I know it's a good question to ask.
Okay, thanks.
It's a bit of an abstract concept, but
thank you very much.
no worries. But yeah, in terms of this uniform grid, that is very much just because, in many ways, because it's easy to define and it's quite systematic. So you can just clearly increase the quality of how you're sampling this space as you add more points to it.
Makes sense.
But the particular points you've picked maybe aren't necessarily particularly meaningful.
Okay.
I also had a question about the k-point sampling. So when you had the thing with the band structure, for that you said you would sample like along the lines, yeah, those red lines, and then you get the band structure out. If you do the sampling with the grid of k-points, what information do you get out that isn't this band structure thing?
Well, you get every point along this band structure that's been sampled is a calculation, I guess. Well, not a calculation, but it's a value where you have a particular k value and you have a particular value of the eigenenergy, the band structure energy for that point. But if you trace out a path like this, you get a nice looking picture where these sections of band structure are all connected, and you can see the way in which these different energy levels are kind of connected together into bands, continuous bands. And this is an important point anyway of how the electronic structure works, because these bands are continuous and they will have a value everywhere in the Brillouin zone. So you can see at certain points in the Brillouin zone bands will overlap, for instance, and that can be quite helpful in terms of understanding some of the physical properties. If you use like a Moncourse pack grid, then you'll have this information, but if you were to plot it, it won't make nice looking bands, it won't make lines, because in terms of this grid, there's no way you can really plot it that looks nice. So if I was to just take this line of points, for instance, I'm kind of taking a path through the Brillouin zone, and I would get a nice looking band potentially. Well, I would if I had enough points. But if I just plot all of these points, then I'm just going to be randomly jumping around this space. And every time I kind of come back and start going across another line, there'll just be a discontinuous jump in the band structure. Oops. So, oops. There's this band structure hiding. If I was thinking of something like this, there'd just be points here, for instance, where I finished a row and I'd started a new row, and it would just the band would just jump to somewhere else. So I guess that's a slightly vague answer, but
Okay, so you do still get energy about the band structure, but you don't necessarily know where like all the individual lines go at every point.
Yeah, well, I'll rephrase it. So you still have all these energy values at different points in the k-space, which is still very similar information, but it's not very easy to then disentangle from that information what the actual bands look like in terms of where bands cross and where bands have minima and maxima.
Okay, thank you.
Because that's the extra information you get out of a band structure diagram like this. This can be quite related to the actual properties the material has. So I just used one simple example in this presentation, but there are other things you can learn from the band structure. One thing you know, though, is whether your material is an indirect or a direct band gap material. So, and that tells you about how the material will interact with light. So if you do a band structure diagram, you can see whether the band maximum and minima are in the same place, in which case light can come in and excite an electron up from the valence band to the top of the conduction band, and that's the process that will happen. Whereas if it's something more like this, then light will interact differently, because it can't, just interaction with light can't push you to a different point of the Brillouin zone. And you need to have some sort of exchange of momentum with a vibration in the crystal or a phonon. But this is similar to what I'm saying here. There is a meaningful relationship between this band structure and the momentum that the electrons have. And it's a little bit, it gets quite complicated to actually fully extract it for many body systems when you're using DFT or using exchange correlation. But generally speaking, we have this idea that how flat or how parabolic these bands are affect how easily they conduct electrons, which is information that would be there in a kind of a Moncourse to Pack style calculation, but it wouldn't be very easy to see the parabolas, for instance. You just see, as I say, the points kind of randomly jumping around.
Okay, thank you.
Hello, can you hear me all right?
Yeah, absolutely.
Yeah, I just wanted a bit of clarification on this diagram that we're looking at.
Yeah, of course. It's quite complicated.
No, it's fine. I'm just wondering, so this K along the x-axis, that's showing the magnitude of the K vector, right?
I wouldn't say that. Well,
Okay.
it's natural to think it means that.
Okay.
So this just like the lattice vectors in the real space cell, every point in the lattice in the unit cell is defined by kind of three numbers, which is going to make a vector position. This is about defining a vector position in this reciprocal space. In this case, it looks like this for magnesium oxide. It's kind of weird shape. But what this is this is a 3D position in this reciprocal space. And what's happened here is it's in this axis is it's been mapped onto just a 1D axis, this 3D path. And the way that's happened is just that it's made up of these line sections. So this is a section here. The length on this axis here is related to how long it is in this reciprocal space. And then you can kind of imagine folding this diagram up and putting it on this red line if you wanted. It'd be a bit hard to see it.
The
So
thing
that's why it's not plotted that way. But.
Okay, the thing I was just not quite sure about is that you have many energy values for each point along your x-axis.
Absolutely.
There's many energy values, and I was just wondering where those multiple values come from. I guess so they're not different paths, or are they?
By a particular point here, you mean? So say this line here.
Yeah.
Yeah. So at every particular point in this Brillouin zone, I have a value of energy. I have like basically what looks like energy levels if I had, say, a hydrogen atom, except they don't represent just one electron. They represent what could be okay. So whenever we're talking about these periodic systems, it's a bit confusing because we're talking about infinite number of electrons because the system is infinitely large. But like what we're saying is what allowed values of energy do these infinite electrons have? And at each particular K point, there is just energy levels of allowed energy that you have. At every K point, you have the same amount of these levels, but where they're positioned is K dependent. And that's what produces these bands. But each like point in the Brillouin zone, at each of these particular, say, K points that I've sampled, I just have an energy spectrum. So I just have discrete values of energy that are allowed and could contain electrons. Is that any clearer?
Yeah, I think that makes sense. Thanks.
Great, glad to hear it, Jack. So, that's part of what we learn from these band structure diagrams, is because it tells us about how easy it is for electrons to move into these different bands, for example. Because conduction of electricity, for instance, is always going to involve moving electrons from a full band to an empty band. or some sort of mixing of bands. And then we just have this panel at the end here, which is the density of states, which is normally much more commonly looked at rather than just the band structure, because the band structure is quite hard to understand. But what you do is you just integrate over all the points you've sampled. In this case, it's along this trajectory. If we're using one course pack grid, it would just be across all the grid points. You just add up how many states are available at each of these energies, and then you get something that looks a bit like this. So it makes a kind of statement about across all the different K points in the system, how many states are available relative to the other K points. And you can, in that case, you can see the bands in terms of places where density of states is non-zero. With something like this MgO crystal, you can say, okay, if the Fermi level is here, then these states are fully occupied by electrons, and these states are not occupied at all, they're completely empty. But this kind of density of states representation is just a compact way of summarizing this band structure information, because the points that are the peaks here are where there's many states available in the Brillouin zone.
Is there ever a time where we'd want information from this full band structure diagram that we can't just get from the density of states?
Yeah, so I did include one example here, which is this idea of effective mass. So if we had a look at a band structure diagram, this is the details that would get removed in the density of states plot. But bands that look like this green band able to conduct electrons much more rapidly, say, than bands that look like this blue one. So like very rapidly, very like peaked parabolas like this is a sign that this band is able to conduct electrons very easily. Whereas there's more flat like structures are a sign that electrons can't conduct very well. So if we were to jump back to this MgO band structure, you can see that MgO has a kind of gentle parabola here for its the bottom of its conduction band. So this is saying that we'd need to compare it to the ideal free gas parabola to actually make the argument that by doing that comparison, we can decide whether this band in MgO is going to be better or worse at conducting electrons than a homogeneous electron gas would be. I can't actually remember off the top of my head whether it's better or worse. It's not one of my examples here. I have to look it up. But probably it's a little bit easier. But that's the most obvious example of something that you can extract from band structure diagrams like this, is some sort of idea of not just how many states are available, but also how easy it is to conduct electrons through them.
Okay, thanks.
Well, feel free to ask if anyone else has any more questions, but otherwise I guess we'll just I'll just run over the most important points to take out of this material. Which is that if we solve the Schrödinger equation under periodic potential, i.e. what we would have in a crystal, then the solutions of that Schrödinger equation will be block waves in the absence of interaction. Although when we introduce electron-electron interaction, it's just going to be a small perturbation normally. And if we understand these block waves, then we can understand where the band structure of materials comes from, which is really useful and important for predicting materials properties. So we ran through some examples today, but it tells us things about how our material will interact with light, whether it's a conductor, whether it conducts electricity, how easily it conducts electrons and things like that. But when we're doing practical DFT calculations, we're always going to be sampling discrete points out of this case space, and we need to make sure we have enough points either to well describe the properties we're interested in, or if we're doing something like a band structure diagram, we need enough points to make the bands come out as smooth lines where we can tell where the band crossings are and what's actually happening. Band crossings just being points like this, for instance, where you can see that there's a band here and a band here, and when they get to this point, they cross each other. But again, that's related to how the material will actually respond to perturbations or electric fields or things. Okay, well, I guess no one's got any more questions. I guess we can leave it there for this tutorial. But I hope that was useful. Yeah, well, I guess I'll close this now. So thanks for joining.